And you want to make some guess for what the likely observation is going to be at that point, and some estimate for the uncertainty that would come around it. And we're particularly interested in methods that give sort of accurate, well-calibrated uncertainties, as well as a best guess at what might be done. This is super important, of course, in problems like predicting the consequences of climate change, where there is considerable uncertainty and you need to take that into account with decision making. Now, the sort of typical deep learning approach to doing this might specify a probabilistic model which looks like this. It might say, I think the output at this location here is likely to be distributed, or will be distributed, according to a Gaussian distribution. So this is what the notation I'll be using to illustrate a Gaussian distribution, with a mean here, which is given, if you're a deep learner, by a neural network. So this would be a neural network with some parameters theta, which takes in the test point where you want to make the prediction and spits out the mean. So this is like what a typical deep learning approach to regression would do. And in addition, we're going to assume we want to return uncertainties as well. So the neural network isn't just going to spit out a mean, it's going to also spit out a variance, which will give us the uncertainty at this point. Great. Okay. And what that might look like after training is shown by this solid blue line, which is like the mean computed at any location xt of the Gaussian after training, and a variance which is shown in light blue around it. That's what we'd like to get out. And typically what you would do is you'd fit the parameters to a training data set. I think probably everybody's sort of familiar with this. For instance, they might use a maximum likelihood approach, and a standard deep learning approach would use a maximum likelihood approach where you choose the setting of the parameters, which makes the target values y that you see maximally probable under the Gaussian probabilistic model that you've articulated above. And typically this would be this sort of maximization would be performed by some iterative fitting method, like stochastic gradient descent or something like that. Now, after training, of course, the parameters of this model depend on the data. So these parameters in here, which I show in purple, the thetas here, which parameterize the mean and the variance function. They, of course, that's the purpose of the fitting procedure, is that the fitting procedure makes those parameters depend on the training data set. So we can write that down below, where the mean after training is a function of the point at which you're querying xt, the test location, and the training data set dc, and the same for the variance as well. If you had a data set this small, applying a standard deep learning optimization approach like above would overfit. It would perfectly put the blue line through all of the data points, and it would shrink the variances to zero. And that's one of the consequences of using this maximum likelihood objective. And it wouldn't tend to generalize well outside of the training regime because it's overfitting as well. It would make confident incorrect predictions across the space. And that's one of the things that we're going to want to cure by moving to this neural process framework. We don't want to inherit the pathology of deep learning that it generalizes poorly with small numbers of data points. And so the philosophy is going to be the following. What we're going to do is we're going to actually cut to the chase, and we are going to specify a neural network which will spit out this mean and this variance directly based on the training data DC. So rather than having an iterative optimization process, which will be used to find parameters, and those parameters give us mu and sigma, and those parameters depend in a complicated way on the training data set defined by the gradient descent procedure. Instead, we're going to articulate a feed-forward neural network which just takes the training data as inputs and spits out the mean and the variance directly. And the way we're going to do that is we'll train it to fulfill that operation by actually looking at lots of data sets. So we won't just consider our data set of interest, we'll consider lots of other training data sets, and that's where this D sub C comes into. The sub C will index those training data sets, and it will learn to learn. So it's a bit like a meta-learning approach. Okay, so there's several things in there. Let's just unpack them over the next few slides. So this is what we're going to do. We're going to directly model the mapping from data sets to parameters. We're going to articulate a model which looks like this, where it has a mean and a variance, which depends explicitly on the training data, DC. And that's going to need some sort of fairly unconventional pieces of deep learning kit. So one thing you might be worried about at the moment, if you've not seen things like this before, is that the size of the training data in here could vary. Like we want our method to be able to handle 1 data point or 10 data points or 1,000 data points. And normally neural networks that we work with, things like multi-layer perceptrons or convolutional neural networks, they take data of a fixed size. It's either a fixed dimensional vector or it's a regular array of pixels in a CNN. And so we instead are going to need to develop an architecture that can take arbitrary numbers of data points as an input. That's our sort of first challenge. And for that, we're going to use this neat paper that perhaps some of you have seen before by Zahir et al., which is called the Deep Set Framework. And they sort of tell us how to build neural networks which are valid functions of sets that can take sets of arbitrary sizes as inputs. And the idea is really simple. It's the paper gives us a theorem, says that any valid set function, so any function that operates on a set, can be expressed in the following way. What you do is you take each element of the set, so that each element here is called an F. So in our example, an example of an S would be a pair of xn and yn. You pass that through a function phi in here, and then you sum that up for all elements of the set. And because this involves a sum here, where you sum over all elements of, say, our context data set here, that means that the order in which you encounter those data points doesn't matter. It's a permutation invariant. And so the resulting function will also be permutation invariant, which of course a function of a set must be. It doesn't care about the ordering of the elements in the set. And so this will sort of do our gubbins, do the necessary computations for us. You have to apply some nonlinearity at the end of this aggregation operation as well. So you apply this nonlinearity row at the end. So any valid set function has a decomposition of this form. In general, this function phi in the middle here will be multidimensional, so it will be a vector. It doesn't have to be a scalar. You can also use other operations here, like min or max, as long as they're a valid operation that can appear in the middle here. Then the proof also goes through. But we're going to use sums pretty much exclusively through what you'll see today. Okay, so we're going to use this theorem to develop a neural network which can ingest a data set DC and spit out a mu and a sigma. And here's how we're going to do that in detail. So let's lift the lid on a neural process and see what bits it's composed of. It's going to have an encoder decoder architecture. So it's going to take in a data set. So on the left hand side here, we have our XY pairs. This is our first data point here, going down to our last data point at the end. Each one of these has to get passed through this function phi. So the first data point comes in, it gets passed through a function phi, and out of that function comes a little vector, R1. R1 is the representation of that data point that will get passed along to a decoder in a minute. And you do the same thing for data point 2, and you get a little representation vector for data point 2 all the way through to the end. And then you sum all of these up. That's performing this operation in here that we saw from Zahir et al. And that gives you a vector here which represents your data set. So we've encoded all of the data set into a fixed dimensional vector. Now we take that representation and we pass it to a decoder. And the decoder takes in R. And then we need to be a little bit careful on the back end here, because we've got a slightly more general problem than Zahir et al. Considered, remember we have to apply this post-nonlinearity rho, but here we need to apply every place that we want to make a prediction. So you take in a prediction location, a test point, a test input point, xt, say xt1 here, and you take xt1 and rho, sorry, if I go backwards. So rho is a function here of r and xtn. And then that spits out the mean and the variance of this Gaussian at each point, at any point that we want to query on here. And that's the decoder. So super simple. Set encoder uses what will be a multi-layer perceptron to get a representation of each data point applied individually to each XY pair. You sum them all up to give you a summary vector of the data set. And then the decoder takes that summary vector and any query location as inputs. This will be another multi-layer perceptron that then spits out a mean and a variance to do a prediction. So let's just have a little look at how that architecture works. These methods were developed originally by DeepMind, by Marta Garnello and colleagues there. And she has this really nice animation, which we've used here to illustrate what happens. Here's the underlying function with some data points on that underlying function, these XY pairs that we want to use to make predictions. Here's a query location at which we want to make a prediction. We take each data point and pass it through the encoding MLP to get the representation of those data points. We aggregate them together using the sum, and then we decode at the test location by passing it through this function rho to get mu and sigma, and then we can get nice probabilistic predictions at those points. So this is the architecture. This just specifies the model. And now what we need to do is we need to train this architecture to do something useful. And it's there that we're going to use multitask learning to do that. This would be a good time if you have questions about the architecture to ask Miguel and line up those questions. Whilst we do that, let's just talk a little bit about training. So training.
We have one question, Rich.
Fire away.
What about the function phi? Are its parameters learned?
Yeah, so the question is about the function phi, if the parameters are learned.
Yeah. So we're going to be talking about learning in a minute, and yes, there's going to be two sets of parameters. There'll be parameters in this decoder here. So these things will have parameters in them. The function phi, the function rho will also have parameters in it that we'll learn, and we'll be learning both of those sets of parameters.
Any other question? No? I think we can.
It's great to get questions, because otherwise it feels like I'm talking into the ether. So thank you for the question. Great. Okay, so that's established what parameters we're trying to learn. How do we go about learning? Well, we're going to use, as I said, plain old maximum likelihood training, but now in this kind of strange conditional model, a model which takes in a data set and its parameters here, the parameters of phi and the parameters of rho, like we've just been discussing, and then wants to make predictions at these other locations dt. And so the way that we're going to do that is as follows. We are going to imagine we're in a situation with lots of data sets, and we'll talk later about how general that assumption is. And it turns out to be perhaps more general than you might expect. But we imagine we've got lots of different data sets. What you do is you sample a data set at random, and that gives you a set of points, XY pairs from that data set. And we're going to take that set of XY pairs, and we're going to split that itself into two sets. We're going to split it into a set DC. This is sometimes called the context data set or the support set in the meta-learning literature. That's going to be our training data. And then there's another data set, DT, which is often called the target set or the test set. And this is going to be where we're going to evaluate our predictions. So even within the training loop, there is a division into data and sort of held out data where we're going to evaluate the model. And the held out data we're going to make predictions for only based on the context set. And then we'll reveal the target set and say how good were those predictions, where we evaluate it according to the log prob of those points that hasn't been passed through the network. So just to be clear, the DCs go through the network and get processed. They make predictions at the target locations, and then you reveal the target values and score how probable they are under the predictive model. And you do this over lots and lots of data sets and average the results and perform iterative gradient optimization of the parameters as much as you would with sort of standard deep learning techniques. So here's some animations of what goes on. So here is a DC that comes in, that's these black dots here. You then make some predictions. This is early on in training, so the predictions are kind of vague. And then you see the target points here, and you say, how probable were those predictions at the target points? And you change the parameters theta to make the mean function and the variances a bit better suited to that particular target set. And then you'd sample another context set, make predictions, reveal the target set, evaluate, and take a gradient step to improve things. This is just fleshes out some more of the details. I'm not going to go through this in detail, but it just substitutes in the Gaussian form that you've got for this predictive model. Other distributions are available. Okay, and this is what training looks like. Epoch 1, this is the picture already seen in the chart. Things are really vague and the model underfits sort of catastrophically. It's really uncertain, so it has big error bars. After epoch 40 of passing through lots of tasks, the mean function starts to go through the context set a bit better and you make more confident predictions on the target set. And by epoch 80, you see behavior like this, where the mean function starts to go nicely through the context set points. The uncertainties come down in that region, but outside of the context set points, you get big fat error bars because it's learned that it has to be quite uncertain about what's going on away from the context set. So you get things a bit like you might expect out of other probabilistic models like Gaussian processes, even though you've only sort of trained them in this sort of deep learning maximum likelihood kind of way. Okay, so that's that sort of wraps up training. This is an instance, as I said, of a meta-learning method because, or many meta-learning approaches use this technique of splitting data into a context set or support set DC, running the meta-learner, and then making predictions on a held out set and using loads and loads of data sets with those splits in order to do learning. In this way, you can see that you're teaching a method to learn, in the sense you're teaching it how to process the context set in order to predict well on the target set. So CNPs are, under this view, are a meta-learning method. They're also a multitask learning method because they require multiple data sets to learn and can share information between those data sets. Good. Okay. If there are any other questions, good time to do prompt Miguel.
We have one question.
Yep.
Yeah, so for training, there seem to be two ways that we could be going, right? We could try to make our CNP be close to the sort of like true target function that we know because of generated results, but we could also try to match the means and standard deviations predicted by a standard Gaussian process that we fit sort of in the normal way to each training task, right? So like if our goal is to just emulate a Gaussian process, but without having to fit it to every new training set, we could also sort of just try to match it, or we could try to match the underlying functions. Can you say something about why we might prefer one way versus the other?
Yeah, so
I heard that, Miguel. That's fine.
Yeah, okay. You could hear it.
Yeah, I can hear that. It's a really good question, and can I come to that in about 2 bullets time or 3 bullets time? It relates to one really important use case of this. In fact, we've done lots of the experiments that you were talking about here. It relates to the sim to real transfer. So I'll just delay that thought for 10 seconds, 20 seconds, and I think I'll get to it. Okay, great. So
we have one more question.
Okay, yeah.
I think this question is also related to some of the questions that the other person just asked. And it is related to like what happens if instead of trying to emulate the Gaussian process, you are trying to emulate the absolute output, then you are assuming that the context is sufficiently characterized as the function that you're trying to learn. So if it doesn't sufficiently characterize the function, and you are not mimicking the output of a Gaussian process, but you are trying to mimic the output of the actual function. So what happens in those cases? Then how much of the noise can it cause?
Okay. Could you summarize the question? Do you want to?
Hi, Rich, can you hear?
Yeah, I can hear.
Okay, so my question is related to what the other person just asked, but slightly different. So like he mentioned one part, which I was also thinking about, like what happens if you have a Gaussian process and you are trying to mimic an output of a Gaussian process versus you are just trying to mimic the actual output. And I'm wondering like what sort of constraint does it put on the context set? So let's say if the context set is not sufficient to characterize the function, that underlying function that you're trying to learn, then like I'm assuming that if you're trying to mimic the actual output of the actual output of the function rather than the output of the model, then what will happen is that if it is not sufficient to characterize the context set, then the model will fit on that noise. And how much noise can it tolerate? And like, would you consider then it to be a natural use case that maybe it's much more useful if you have that kind of noise, or if the number of context points are not sufficient to characterize the function, to use a Gaussian process output rather than the actual outputs?
Great. Okay. I've tried to delay answering the first question, so maybe I'll answer the first question and then answer this one. Okay. So one use case of this method is in sim to real, or you can use it as an emulator, and I'll show you some experiments like this later on. So imagine that you actually believe your data come from a Gaussian process, and you know what the covariance function is, the form of the covariance function, and maybe know the hyperparameters. It's still potentially useful to use a neural process to emulate that GP because it's much faster to execute. So these things do not have cubic scaling for number of data points. In fact, they're linear, which is far better than GPs. So one trick you can use is you can sample data sets from lots of GPs with your covariance function of interest. You could vary the hyperparameters between those realizations of data sets, and that will include picking the number of data points in each data set that you want to have in your training loop. And then you can train a neural process to emulate the GP. And once you've trained it, you can then deploy it on real data, on the real data that you actually wanted to apply the GP to start with, and it could potentially be faster. So when you're doing that procedure, you should try and match your context set sizes to be roughly covering the sorts of sizes that you'll see in your downstream task. So if they've all got thousands of data points in them or hundreds of data points, you should have hundreds of data points in the context sets that you use for training. If your underlying function is really, really complicated and you only have a few data points, there won't be enough information in a small data set to pin down the underlying function. But generally in GPs, the functions are local. So if you have some data points in a particular region, that'll actually learn the function in that region. And it doesn't matter you haven't got data points elsewhere, because all bets are off in those regions anyway. And as long as it learns how in a particular region to go between context set and function, we have methods that I'll tell you about, which then can therefore extrapolate elsewhere to fill in the function based on the data in those regions. So you sort of want to make sure that your context sets have similar density of points as you would see in the downstream tasks. And in general, when we're training them, the number of data points in your context set is another random variable that you sample over during training. So sometimes there's no data in the context set at all, and you're essentially learning the prior. And sometimes there are hundreds, and there'll be everything in between. So we sort of randomize that during training. So going back to the first question, when would you want to do the sim to real thing, and when would you just maybe want to use real data to train your neural process? It really depends what you think is going on. So if you think the data are non-Gaussian, and so it's not well described by a Gaussian process, maybe there's heavy-tailed noise, or the underlying function is not joint Gaussian distributed, maybe it's asymmetric, for instance, which GPs can't be. And you've got a pile of data, then it's useful to train on that pile of data. If you really think everything's a nice matter and covariance GP, and you can bear the compute time, and you've not got tons of data, then you should use a GP. So it's a question of how much data and whether it really is GP distributed, And do you need to scale up your GP? And is this a valid way of scaling it up? Those are the sorts of questions in mind. I should say that this sim to real idea, let's just fast forward here, is not limited to training on GPs at test time, training time. It can be trained on any simulator you like. So you could train on, in this example, for instance, we were ultimately cared about predicting on a set of measurements that were made in Canada of the lynx population numbers and the hare population numbers. So lynx predate on hare, and if there's lots of lynx, then there don't tend to be much hare around because they get eaten a lot, and vice versa. If there are no lynx around, then there's lots of hare around, and you get one of these predator-prey curves where the populations oscillate out of phase of one another for that reason. So what we did is we took a sort of a classical predator-prey model, and we instantiated it multiple times with lots of slightly different parameters for that predator-prey model, and we trained a conditional neural process on some of those data and asked it to predict over held out regions these test set points, so just the training loop that I showed you before. And then we can take it from that simulated data and apply it directly to real data, and it makes fairly nice predictions on these real data points. This is a data set it's not seen before, the real data set. And in regions where we don't have any measurements, we removed a little section of the real measurements here. You can see you get fairly nice interpolations with good error bars. So the CNP has distilled all the information in that simulator down inside the neural networks and is actually able to do something the simulator can't do, which is to make probabilistic predictions and forecasts and things like that, or impute missing data. So this is sort of a more general view of this sim to real type architecture. Good. Does that answer the two questions that we had from the audience?
I think kind of.
Okay.
I think in the interest of time, we can continue.
Yeah, great. Okay, so other places where this is useful, data sets are small size where overfitting is important. So these things will not overfit because they use held out sets to evaluate the predictions. In fact, in general, they underfit a little bit, but overfitting is not an issue for these things. They're also really good for data sets that have variable and complex patterns of missing data. So in general, typical deep learning substrates, if you think of CNNs, MLPs, transformers, things like that, they operate on data, tend to have fixed size. So if you think of an MLP, it's a fixed length vector. We don't have substrates that can deal in general with things which are regularly sampled. So if you think of like weather station measurements that happen at arbitrary points in latitude and longitude, we don't really have a deep learning primitive that naturally can take in off the grid data like that, but CNPs can do that. So I'll show you some examples from environmental science where we're using them for these sorts of purposes. Another natural thing that they give you out of the box is the ability to do continual learning. So imagine you've seen a bunch of data points so far. Maybe you've just seen these data points at the top here, and you have a representation for them, but then somebody says, oh, we've got this extra data point that's just come through in our weather recording station. Can you add that and update all your predictions? And can you do that without revisiting all of the old data that we've had before? Because this is all computed by this sum, we can just do a running sum here where we just compute the representation of the new data point and add it to the representation from the old ones. And we've automatically updated our representation of the training data set. We didn't need to revisit all of the individual data points like you would with a standard optimization procedure. And so out of the box, this gives you what's called online learning, or more generally continual learning. It naturally supports sort of low cost incremental updates. The final thing I wanted to point out here is it's really good for on-device learning. So there's some work to put these methods actually into satellites at the moment, and also mobile phones. Typically, hardware like that cannot support backprop. Backprop is either energetically too expensive, runs down the batteries on these things too much, and more likely than not, like standard operating systems on a phone just don't support backprop at the moment. So you can't do on-device gradient-based updates. In order to apply the CNPs at test time, once you have trained them, it doesn't require derivatives. It just requires passing things through a neural network in a feed-forward way. And so you can train things centrally and then deploy the learning algorithms on the device, on the satellite or on the phone, and it will support learning without requiring derivatives. So that's another benefit. Okay, so that's some use cases of neural processes. I want to just talk a little bit about drawbacks of current CNPs before I talk about some of the work that we did to address them, and then I'll just end with lots and lots of examples of how to apply them. So there are two problems with them at the moment. The first one, from the original work, I should say, the first one is that they severely underfit. So here's an example of taking a nice conditional neural process and applying it to a small data set, which did come from a GP. This is the underlying GP. And here's what you get out of a neural process. You can see that the neural process doesn't go through the data points like the GP did, and its mean function is off. It's a bit vaguer than what should be going on, and it's not moving around as much. It should do that mean function, so it's underfitting. And secondly, perhaps more egregiously, they did not extrapolate well. So what do I mean by that? In training, you have to specify some range of inputs that you're going to expose the CNP to. So here's a CNP that we've trained in this range, and we're going to expose it to this data set. And in this case, it did reasonably well on this particular data set, making reasonable predictions. But we're going to now expose a little bit more data, which is outside of the training range. Let's see what happens after we perform one of these incremental updates. You can see that, well, maybe it's sort of modeling the new data points okay, but it's on catastrophically wrong on the old data points. So the mean function, which was looked reasonable before, is completely in the wrong place, and the uncertainties are kind of crazy too. So in general, these methods did not extrapolate well. This is the original stuff from DeepMind. And so one big step forward in this area came from my group, which was to build translation equivariant CNPs. And the basic idea is very similar to CNNs, like the move from multi-layer perceptrons to CNNs. In that case, we knew that for images, we should build some translation equivariance in, i.e. if you translate an image 1 pixel up and 1 pixel to the right, you want all the feature maps to translate in a similar way, and CNNs sort of have that built in. So the representation inside the CNN is called translation equivariant. If you translate the input, you translate all the representation through. And if you pull over an equivariant representation, if you pull over the space, then you get an invariant representation. And at the time when people were doing this for images, they're interested in obviously good classification performance of images. And if you translate an image, the class label should stay the same as long as you don't translate it too far. And so building equivariance into CNNs and that yielding invariance was a really sensible thing to do. It cut down the number of parameters in that CNN because you have lots of effective weight sharing. It gives you less parameters to estimate, fewer parameters to estimate from data, and gives you better performance. So we want to do exactly the same thing for CNPs. So let's just explain in a bit more detail what translation equivariance means here. So here's another little toy data set at the top here, and we're going to go and translate that toy 1D data set how time steps, let's say to the right. Let's imagine the x-axis here is time. We've just translated it over a little bit. That's what this operator T does, which has an argument tau, which is the amount of the shift. If we take the off-the-shelf Garnello et al. CNP and apply it to these two data sets and look at the predictions we get out, this is the prediction we get from the top one, this is the prediction from the bottom one, and maybe on this fuzzy Zoom call you'll be able to see it. If I then translate the predictions on top of each other, you can see that they don't really line up. The uncertainties are sort of a way off, and the mean functions are actually a little bit different themselves. Now, if you believe that your underlying stochastic process from which these data sets come from is stationary, i.e. the statistics are translation invariant, then your prediction map should have the property that if you shift the inputs like we have done on the left-hand side here, then your outputs should shift in the same way and be translation equivariant, and they aren't in this case, which is a problem. For a GP, everything would translate beautifully if you had a stationary covariance function. So what we wanted to do was to build into the CNP this translation equivariant structure, so that if you did believe your data came from a stationary stochastic process and not necessarily a GP, could have higher order statistical dependencies, things like images, for instance, or weather, for instance, then you'd be able to use this structure and it would learn much more efficiently. And the way that we did that, I'm just going to explain for about 30 seconds before we start talking about results, is as follows. So here's a little data set again, and here we've applied the translation operation to give you this translated data set at the bottom. What we realized fairly quickly on is that the encoder is where the action is. The encoder and the representation in the encoder is the thing that we need to fix. And this fixed length vector representation we had to start with, where we encode a data set into a vector, we couldn't work out how to build translation equivariance into this. There was just no natural way to do that. We were kind of stumped. And the breakthrough happened when we realized that the right way, or perhaps the only way to view this problem, is instead of thinking about embedding data sets to vectors, we instead embed the data set into a function. So we'll take a context set on the left here, this is this DC, and we'll embed it into a function on the right-hand side, which is a function of the input space. Because now we've got the inputs explicitly in our representation. If we translate all of the data sets, then we would if we translate the data set on the input side, we'd like this function to translate in exactly an analogous way, just translate tau time steps to the right. So this was sort of a key insight, that we needed to take CNPs, move beyond this vector-based embedding to think about embedding into functions. And again, there's this sort of connection to Gaussian processes, or thinking about functions rather than thinking about finite dimensional quantities, that's at the heart of these methods. Okay, so here's how we did that. So we have to now redefine or redevise an encoder. And the encoder before used this deep set framework. And in order to handle translation equivariance, we needed to come up with a generalization of that kind of concept that would handle equivariance. And that's this thing that we call a convolutional deep set. This is like the workhorse of what's going to be the convolutional CNP, which I'll show you in a minute. I'm going to sketch what's going on in terms of the convolutional deep set. So if you remember the original deep set representation, this had this function rho, which was an MLP that got applied to the encoder representation. This was the vector R, which came out of the encoder. And that gave your function of the context set. In our case, rather than having an MLP for rho, we're going to have a CNN. And the CNN naturally is translation equivariant. If you translate the inputs, you translate all the feature maps and the outputs of the CNN. Okay, so that's what we're going to do for the function rho. That's sort of the less interesting bit. Let's talk about the encoder bit itself that's inside the function rho. In the deep set case, we had these functions phi that you had to sum over. You had to apply to each one of your data points and then sum over them. We're going to get a similar construction in the convolutional deep set. It also needs to be permutation invariant, I should say, just like the original deep set. That's why we're having to sum over the components of the training data set. But the function we apply is more restricted. You have to apply this function psi to start with, which depends on just the difference between the data point x and the point x prime, which is in this functional representation of your data set. And it's because of this structure phi that you'll end up getting translation equivariance popping out, because it only cares about differences between x and x prime. This looks a bit like a convolution, although it's a sum over a discrete set here rather than a continuous set. And then you also apply some nonlinear transformed outputs as well by this function phi sub y. So that's the new form of the encoder. And what we were able to prove was, in the original deep sets case, this is any way to represent a permutation invariant function, i.e. a valid function on sets. On the right-hand side, we proved that any valid set function, which is also translation equivariant, has a representation like this. So any of these functions can be represented in this way. So it's sort of a universal approximation type result. Okay, that's all I'm going to say about theory, and I'm going to go through a bunch of experiments in the last 10 minutes or so. So let's just check that this does give you translation equivariant in practice. So let's take our data set, do the test where we translate it, and look at the predictions. These are the two sets of predictions. If you now map these on top of one another, you can see they're just lining up bang on. It's doing what it says on the tin. So that's good. And we can see that this bleeds through and gives you good fitting of data sets now without underfitting. So on the left-hand side here, we see some results where it's emulating a squared exponential GP, and it's going nicely through the points, and you get good uncertainties coming out. On the right-hand side, you're doing something that a GP can't do. It's modeling a sawtooth function. And again, it's getting, you know, good predictions on that sawtooth function with nice asymmetric behavior. And what's more, it doesn't only tend not to underfit, it tends to extrapolate really, really well as well. So if we train in this limited training range here, shown by the dotted lines, we get good predictions, like I've just shown you, inside that training range. But if we now expose it to data outside of the training range and do an incremental update, we get nice, sensible behavior. It's making just as good predictions in that region as it was in the original region because of the equivariance property. It doesn't care where the data is anymore. Everything's sort of equivalent because equivariance is built in. Okay, so that's sort of two perhaps not so interesting results. Here I'm going to show you some results again on GP data. So this is again the question of, can we emulate a GP? At the top here is a periodic GP. The Oracle GP is shown in green, like fitting the Oracle model on the data is shown in green. On the bottom is a Mattern covariance GP. Again, the Oracle is shown in green. And we're going to expose more and more data points over time and see what the model's predictions look like. And I'm showing you samples here. These blue curves are samples from the CNP, I should say. So the blue is samples from the CNP, and the green is the sort of ground truth here. And what you can see is it's learning pretty well to emulate the GP, and it's sort of behaving rationally with small numbers of samples, even though it's sort of a deep learning method. Good. Okay, so that's sort of 1D things. Let's try and take it to regions where GPs aren't so good. So let's use this sort of toy data set, which was also used by the DeepMind crew to start with as well, where we're going to view MNIST as a multi-task regression problem. So the way we're going to do that is we're going to take pixel locations here in the horizontal and vertical direction as the inputs. So we have two-dimensional inputs, and then the pixel intensity will be Y. So we're going to view each image as a little sort of 3D regression problem where the location of the pixel is X1 and X2, and then the grayscale is the Y value. And that will allow us to do things like this. We'll have a context set, which is shown as the white and black pixels here. That's a subset of the pixels from the left. That's the things which aren't blue, and the blue things will be the target set. So we'll say, take a few pixels from this MNIST image, we'll reveal those few pixels and get it to predict the masked pixels, the pixels in blue. So that's just sort of labeling that more formally. And this is what sort of the reconstruction you get in that case once you've trained a CNP on multiple images. So each image here is a task, and you can see you can get reasonable reconstructions to this. So this would allow you to impute missing values in an image with arbitrary patterns of missingness. So that's a cute trick. Let's look at the equivariance property here quickly and see what it buys us. So remember, the training images in MNIST, of course, are these nice centered digits. Let's go and expose it to test images which have multiple digits present. If you don't have equivariance built in, you're going to find this problem really, really hard. And we took the best-in-class method to try and impute these context sets here, which is called the attentive CNP, which is another model from DeepMind, and it gives you terrible in-painting results because it's only ever been exposed to these training images, which were nice centered MNIST digits. So on this example, which is sort of clearly a couple of ones, it's making this funny fuzzy prediction in the middle. If you take the CNP type model that I'm talking about here, in all these cases, you get nice predictions. It doesn't care where the digit is or how many digits there are. It can impute them nicely because it's got translation equivariance built in. Sort of a nice property. Here's an example of the same thing on Celeb A. And on Celeb A, we're going to expose it to more and more pixels and ask it, here's the predictive mean here. As the number of pixels increases that it's exposed to, these are the standard deviations. And this is a cubic spline baseline to show you that the cubic spline method doesn't do a great job either. And you can see the CNP model is doing reasonably well. It's giving you nice, sharp reconstructions, even when only 5% of the pixels are revealed. So you can train this thing on celebrity images, and you can play the same trick that we applied to the MNIST digits, whereby we expose it to an image with multiple faces in it. And here, this is an image with multiple faces in it. And we've got, I think, roughly 2 or 3% of the pixels here exposed to the method. And you ask the CNP to fill this in. It's never seen more than one image in a more than one face in an image before, and yet it's able to interpolate this out, and you can sort of clearly see a Bradley Cooper and Ellen, a Jennifer Lawrence, etc., Julia Roberts. So it works quite nicely. So these are sort of cute sort of demonstrations of the benefits of translation equivariance. I want to say just a couple of words about our efforts on the climate side. So we've been using this structure to handle off the grid in climate. And one really important problem in climate is to take runs from a climate simulator. So we use a big physical model to predict what the climate might be in say 10 years time. And you combine that together with actual observed weather measurements in order to make high fidelity predictions on a much finer grid. So originally these climate measurements that come out of a simulator can be on quite big grids, both in time and particularly in space. So there might be 5 kilometer by 5 kilometer grids or bigger than that. And there's sort of a cottage industry in taking those quite coarse predictions from the climate model and putting them onto a much smaller grid size. So you can make predictions at particular points about what's going on. And the way that they do that is they combine real observational measurements from weather stations, say, across the world to learn what the mapping is from the climate simulator to actual observed weather. And you get predictions from the simulator for the last 100 years, and we've got weather recordings for the last 50 years. We can put the two together to learn what the relationship between the simulator, say predicted temperature is or predicted rainfall is, and the actual rainfall. And then we can use that relationship in the future to try and guess what the weather would be like in 5 years' time, say, based on the climate simulator results. And that's really important for predicting, like, are there going to be big floods, or are there going to be extreme, really hot weather events in particular locations, and using it for planning purposes. So in this work, we looked at predicting temperature and predicting a harder variable, which is precipitation. And we used the CNP that can naturally take off the grid data and use it to make predictions wherever you like, which is something which the climate community didn't have in the models they could do at the moment. You get nice predictive means. This is showing a close-up over Germany here, and you can even produce samples of what weather will look like. And here there was sort of considerable uncertainty, so the samples in this temperature field vary quite considerably around the mean by 2 or 3 degrees. And if you evaluate this thing, the new methods we developed are sort of beating the benchmark, more classical methods for this sort of downscaling task. Here you use sort of real data from the last few years to evaluate your method as a held out set. Cool. In the last couple of minutes, I want to really sort of whiz through applying this to classification as I sort of promised to start with. And I'll just give you the high level ideas of this. We've not got too much time left. In classification, we're going to want to use a state-of-the-art image classification tool. So we're going to use a CNN, and we're going to adapt to CNN according to a context set to solve the task that we want. So here's a task. The task has two categories. It has cats and dogs, and the context set is going to comprise 2 cats and 2 dogs. It's going to say, train on that, adapt your CNN to then do predictions so that if I query it with a new cat or new dog image, you can tell me whether it's a cat or a dog. And the way we're going to do that is as follows. We're going to use the context set to adapt the future extractor. There's this really neat, lightweight way of adapting a CNN called a film layer that has very few parameters that we can use to adapt the components of a CNN. We'll use that, we'll take the context set, that will adapt the body of the CNN, and then we'll take the cats, pass those through the adapted body of the CNN to generate the head of the network, which will be a linear classifier. The cats will generate weight 1, and we'll take the dogs and pass them through, and they will generate weight 2, and so on and so forth. If we had more classes, we would develop more bits of the head. So that's going to be a method for adapting the network, and then we can pass through a new input that the network hasn't seen before and get it to classify it. So here's an example of this system. This is the training set. The training set comprises the class stopwatch. It's got 2 images of stopwatch. Digital clock, it's got 3 images of a digital clock, digital watch, parking meter, etc. Here's the test image. The training images are used to adapt the CNN. It's very low shot. It's extremely low shot, right? This is a very challenging problem. And these test images don't look a whole lot like the training images. So it's really hard. You have to learn quite a lot about the structure of digital devices to actually solve this properly. Here's the results from the method I've just shown you. And just thresholding the ones with the highest probability, we get this one correct, and 2 wrong. So 50-50 maybe to start with, not so impressive, but we can do a nice thing. We can add in a new image of a parking meter. This image of a parking meter had lots of text in the background, so it's a bit confusing. And we can do an incremental update, like continual learning, and then it starts to get the parking meter thing correct with a second image of a parking meter, which is a bit like this one. And we can even add entirely new classes in to an incremental update. So here I've added in a sundial image, and it's getting the sundial image correct as well. And now it's getting 4 out of 5 things correct, which is perhaps not so bad given the difficulty of the task. And this wasn't cherry picked. This is a fairly indicative task of the sort of thing this can do. So it's able to do pretty accurate few-shot learning. And in fact, if you compare it to the state-of-the-art methods in this space, it's the state-of-the-art system on this data set called metadata set, which is typically used to evaluate few-shot learners. These are methods from Google, which use fine-tuning. These are the state-of-the-art fine-tuners out there. They're 40 times less efficient in terms of the compute time it takes to adapt. And the method I've shown you, which is a conditional neural process, is able to get fairly accurate results on these few-shot learning tasks. Great. I'll end there just by thanking a really fantastic team. I think I've got all of them here, but all of these people are responsible for all of the hard work that I've shown you over the last few slides. And I'll just leave up a summary and a list of references. So I won't go through them. I'll share my slides with Miguel and he'll put them up. And if there's time, I'm happy to take any remaining questions.
I think we have time for some quick questions. Do we have any? Yeah, I'll pass just the mic, and you can just talk to Rich directly.
Hi, very interesting work. I was just wondering, the convolutional CNPs, do you think this is very similar to the equivariant graph neural networks?
Yeah, it's similar. So some of the architectures that we use are similar. There are a few different types of equivariant neural network, graph neural network. The ones that I know about do not use convolutions in the same way that we've used them. And in fact, the ones from Max Welling's group that I know about have a higher, might be easier to apply to high dimensional problems. So we've really looked at 1- and 2-dimensional problems for equivariance, but in many places you want to be equivariant in many different ways, like to rotations, for instance, as well as translations. And there, the representation that Max uses to do it in their work would be better than the representation we use. The graph neural networks, so they have a different structure for handling the equivariance. It's done in a slightly different way. It will be worse, I think, for translation in space and time than our method, but it'd be better for high-dimensional problems. They're also not trained in this like meta-learning type way, so that's the other point of difference. They tend to be more trained in a conventional way, whereas we're doing in this like leave one out kind of way, or leave several out kind of way, which makes them better for few shot learning and sort of getting well calibrated uncertainties and things like that. So there's the two differences, but the ideas definitely could be combined, and there's certainly some of the things we've been thinking about doing.
Yep, I was also thinking about the EN equivariant graph neural networks from Max Willing's group. So yeah, that clarifies. Thank you.
Great.
We have maybe time for one last question. Yeah. Can you repeat louder? Yeah, if you use different aggregation functions, what happens? That's the question.
Yeah, so I think the aggregation function you use has to be picked carefully depending on the use case. So if you think about like a more typical use for these aggregation functions, so for instance, in computer vision, they're used often if you've got multiple cameras. Maybe you're looking to detect whether a single object is present over multiple cameras. So in a phone, in a self-driving car example, maybe you want to detect whether the road is icy, and you've got 10 cameras on the car, and what matters is if only one of those cameras shows something which makes you think it's icy, you want to give a warning to the driver. In that case, you'd use an aggregation function, and it would be better to use a min or a max, because you want one camera to like veto everything else and say, no, I've seen something icy. And so if any one of us sees something icy, then the driver needs to know about it. So you use a max function. In our case, you don't want one data point to dominate your representation of the data set, because typically the data points are all spread throughout space, and each one is telling you something locally about the function. If you took a min or a max, you end up with one element in your vector of just coming from one of your data points, and that is a really inefficient way of representing stuff across the whole of space. So typically we've used sums with that intuition, and they tend to perform a bit better. Maybe there are certain classes of function and particular examples where a min or a max or some other operator would do better, but we haven't found them yet. It's not something we looked at sort of in massive detail, but I would imagine sum is pretty hard to beat.
Good. We don't have more time. Yeah, I just want to say thanks, Rich, for joining us remotely, and yeah, let's stay in touch. Thanks. Bye.
Thank you.
Bye.
Thanks, everyone.